Welcome to lecture number 8. This will be a quite short lecture, but I just want to complete the topic with the transient circuits. When we remember the last lecture, we had this circuit here, and we wanted to calculate the voltage at the capacitor. And therefore we analyzed the circuit and we got a differential equation which looked like this. And this differential equation included a time constant. We called this tau. And after that, I told you that the problems we will have a look at in this course will always lead to such a differential equation, and the result will always look the same like this here. Okay, and then we found with help of the boundary conditions the values for our constants k1 and k2, and that gave us the final solution. And when you remember finding the differential equation and finding the time function were absolutely independent from each other. The only reason we needed the differential equation was for tau. Okay, couldn't we save all the work with the differential equation if it's only there to find the value of tau? There is a way to get tau directly from the circuit, and today I will show you that trick. Okay, again, this is the circuit from our last lecture. And we found out that tau looks like this. It's R times C. Okay, and in the circuit there was a switch and we closed it in the moment t equals t0. And now I will redraw the circuit for the situation after closing the switch, and I will deactivate all sources. That means we have an ideal voltage source in our circuit, and if I deactivate it, it becomes a short circuit. Therefore, our circuit looks like this. The source is deactivated, the switch is closed. Okay, let me rearrange the two elements a bit and now have a look. Our time constant tau depends out of C and R. Okay, let's go to the next example. From our last exercise class, we had this circuit here. Again, we closed the switch and found out that our time constant tau looks like this. And now let me redraw the circuit for the situation that the switch is already closed, and I will deactivate the source again. So our circuit looks like this. And now I rearrange the elements a bit. They're all connected in parallel, and therefore the order of the elements does not matter. So I draw it like this, and now have a look. The time constant tau consists out of the value of the capacitor and the value of the parallel connection of the two resistors. That is interesting. Let's go on to the next example. From last exercise lesson, we found out here that tau looks like this. And again, I deactivate the source of the circuit, I close the switch, and then the circuit looks like this. And now I rearrange the elements again, so the circuit can be redrawn like this. Okay, and now this is our capacity, and this here is the total resistance from the point of view of the capacitor. Okay, last example from our exercise class. We had this circuit, we opened the switch, and this time we have an inductor in our circuit. And we found out that tau is L divided by R2. And now again, we analyze the circuit when the switch is flipped. This time when it's opened, we deactivate the source, and this is what is left from the circuit. And again, this time we have L and divided by the resistor value. Okay, maybe you have noted this now. If we want to find tau directly, we have a look at the circuit after the switch is turned on or turned off. Then we deactivate all the sources. And if we have a circuit with a capacitor, then we analyze the total resistance of the circuit from the point of view of the capacitor, and our time constant tau will always be the total resistance multiplied with the capacitor value. And if we have an inductor in our circuit, then we again find the total resistance, this time from the point of view of the inductor, and tau would be L divided by this total resistance. So this was the last trick I wanted to show you. We are finished now with that topic. And now, please use the rest of the lecture time to do the training tasks on this topic.